The goal of today's lab is to give you guys a feel for what is quantum mechanics. Throughout the fall semester and the spring semester, we only talk about the world of classical physics. So in today's lab, there are two introductions, and within those introductions, I tried to give a very brief overview to the question, what is quantum mechanics? So I want to be very explicit right now. You do not actually need to use any equation from the introduction in the labs to actually perform today's lab. I use notation called Brockett notation that we never talked about. There are some differential equations in there. There's some commutation relations. There's a lot of stuff in the introductions. And again, you don't need the stuff in the introduction to perform the lab. All the equations you need for today's lab are after the introductions. But I decided I wanted to still kind of give you a feel, show you an equation, kind of describe what that equation is saying. So if you feel you're getting lost, don't worry about it. There are entire year-long courses devoted to talking about those topics. I just tried to give a very brief overview of those ideas. So, what is quantum mechanics, and what's the difference between quantum mechanics and classical mechanics? In Physics 121, we spent an entire semester talking about how classical mechanics works. So what's the difference between classical mechanics and quantum mechanics? Sometimes if you hear the word quantum mechanics, you might think the physics of the very small. So you think something like particle physics or atomic physics. But it's not really correct to say quantum physics is the physics of the very small. It is true that quantum behavior is often very apparent when you're talking about very small objects like single particles. But there are cases where macroscopic physics, so physics that are potentially big enough you could see with your eyes, where objects that might be made of millions of molecules display quantum behavior. So there are examples like in superconductors, a type of conductor that doesn't just have a small resistance but has exactly zero resistance. There is quantum mechanics on a macroscopic scale in superconductors. A Bose-Einstein condensate state is a state of matter. So you might have a state of matter consisting of millions of atoms, and those millions of atoms as a state of matter, as a big chunk of stuff, are displaying quantum effects. So often quantum mechanics is related to the physics of the very small, but that's not entirely going to be true 100% of the time. There are cases where quantum mechanics can be seen on big scales too. So what is quantum mechanics? What's the difference between quantum physics and classical physics? To address that question, I'm going to say right now that a theory will become quantum when your commutation relations become non-zero. But right now that doesn't really mean anything because I'm using words that we haven't really talked about. So to give a feel for what quantum mechanics is, let's do a thought experiment. This is a thought experiment that in principle we could have talked about in the middle of September, because all we need to know is 1D motion to consider this thought experiment. So we're back in the middle of September and we just learned about 1D motion. So let's suppose I have an object and that object is moving, and this object will have some speed. Okay, and some velocity. So, okay, this object has some velocity, and we're going to ignore acceleration. So we'll say this object has zero acceleration. So this is going to really be a really simple 1D motion problem. We could say x is equal to x initial, v naught xt, 1/2 axt squared, but we already said ax was 0 anyway. So this is a really easy 1D motion problem. Now, if I wanted to, I could ask the question, where is this particle? To answer that question, colloquially, you would just say, well, you look to see where the particle is, and then you know where the particle is. And that is true. If I want to be a bit more thorough in how I answer that question, I could say, well, if I want to know where that particle is, I would need to perform a measurement to determine the location of that particle. And then after I perform my measurement, I would know the location of that particle to within a certain error range. Now, when I just look at the particle, that is one example of performing a measurement. My eyes are not perfect, but they're pretty good. So I could look at where that particle is, and I could say the particle is located here, and I have some error bars on my measurement because my eyes are pretty good, but they're not perfect. Now, maybe instead of using my eyes, I spend a lot of money, get some really elaborate measurement device, and I could know the position of this particle to a much better degree of accuracy. So in doing that, I could shrink the error bars. And let's pretend, for the sake of argument, I shrink my error bars down to 0. So I perform a very expensive measurement, and I know exactly where this particle is. Now, it doesn't matter what this particle is. It could be anything. It could be a proton or a rock or a shoe. It could be anything at all. I now know the position of this particle after I spent all that money on that phenomenal physics equipment to a perfect degree of accuracy. Now, a minute later, the particle has traveled some distance, and I decide I want to know what is the velocity of that particle. Or actually, no, let's move on to late November. I want to know the momentum of that particle. Well, knowing velocity, that's very much like knowing momentum. They're practically the same question. So I want to know the momentum of this particle. So I could perform some type of measurement. I could, in principle, get a really elaborate equipment, and I could perform a measurement of this object's momentum to a phenomenal degree of accuracy. So at this point, I measured the object's momentum, and now I know momentum to a phenomenal degree of accuracy. Later on, I could ask, where is this particle? So I wait a little bit later. This particle is still moving in the same direction. We assumed 0 acceleration throughout. And if I measure the position of the particle again, I could predict exactly where the particle is. I know how to treat 1D motion problems, so I could say the particle will definitely be right here because I calculated it. And then I take my really expensive measuring device, I performed a calculation, and when I take my really expensive measuring device, I will measure that particle's position again, and that particle's position will perfectly agree with my prediction of where it's going to be. So at this time, and then later on, I measure the particle's momentum again, and well, there were no forces on this particle, so the momentum is going to be exactly the same thing as what I measured back here. So at this point, I'm just wasting my time. I know the position, I know the momentum, I know how to predict the position, I know there are no forces on this particle, so the momentum is going to stay constant throughout. In classical physics, everything I described here is perfectly okay. Let's perform the same thought experiment, but let's perform this thought experiment in the realm of quantum mechanics. And how would this thought experiment be different if in the world of quantum mechanics? So in this thought experiment, I am going to say begin by saying I have a particle, and I know that particle is moving to the right. At this moment, I don't really know how fast it's moving yet because I did not measure its momentum yet. I don't know where the particle is yet because I haven't looked yet, or I haven't performed any type of measurement. So the first question I'm asking is, I know it's moving to the right-ish. So the first question I'm going to ask is, where is that particle located? What's its position? So I get my really expensive measuring equipment. I will measure the particle's position, and I find that the particle's position is right here. And I find that position to a phenomenal degree of accuracy. Now I know the particle's moving to the right-ish. I don't yet know what its momentum is, but okay, whatever. It's not too hard. I have a really expensive equipment that could measure momentum to a great degree of accuracy. So I take that really expensive momentum measuring device and I measure the momentum, and at this point, I know the momentum, and I know that momentum to 100% accuracy. Arbitrary, as accurate as you want. You have a billion decimal places accuracy in your measurement. Here's where quantum mechanics is going to become a thing. If I were to measure that particle's position, well, in the previous example, we knew the position, we knew the momentum, we know how to predict the position from 1D equation of motion, and when we go to measure position, we find exactly where the particle is located. If I go to measure that particle's position, that particle's position might be anywhere in this range. So that particle's position on average is going to be here, but it might be a little ahead of where it should be, or it might be a little behind where it should be. So that particle's position, it's almost like the act of measuring momentum smeared out some of the knowledge about this particle's position. So I could say, I knew what the momentum was, I knew how fast it was going, but I kind of lost information about the initial position. So my V naught X is fine, I know that, but I'm a bit hazy now on what my X naught was. I mean, I could remember what X was, but it's kind of like the momentum smeared out knowledge of the position. So the particle might be over here, or might be over here, might be somewhere here. And then, okay, let's suppose I measure the position perfectly, and when I measure the position, I measure it to be here to a perfect degree of accuracy. Well, if I go to measure the momentum a bit later, the momentum, I might measure the particle moving kind of slow, or I might measure the particle moving kind of fast. So the momentum might have changed a little bit. So what did quantum mechanics do in this thought experiment? Measuring position to a phenomenal degree of accuracy kind of blurred momentum. And measuring momentum to a phenomenal degree of accuracy kind of scrambles up the knowledge about the object's position. Now, this is the way nature works. In classical physics, you can know position to a perfect degree of accuracy, and you can know momentum to a perfect degree of accuracy. In quantum mechanics, if you know a phenomenal degree of accuracy of one of those quantities, it kind of blurs the other. The way this is represented in quantum mechanics is through commutation relations. So the question we were originally thinking about is, what is the difference between classical physics and quantum physics? When does a theory of physics go from classical to quantum? We live in the classical world. We're used to projectile motion, the mechanics we talked about in 121. We're really big objects. We're made of many particles. We don't really see quantum mechanics in day-to-day life. So it is foreign and weird to us. The way we represent this is we say, if I say X and P for momentum and position, formally in quantum mechanics, X and P, position, momentum, are what's known as operators. Operators wear the hats there. So this is basically saying, if I measure position, if I have the position and the momentum operator, subtract that, the momentum and the position operator, In classical physics, these will just be 0. So that's like saying xp minus px is equal to 0. So I could say xp is equal to px. In quantum mechanics, this is no longer true. So in classical physics, this relation would be true. In quantum mechanics, this relation is no longer true. And as a result of this, the reason, or a consequence of this commutation relation being something other than 0, is that measuring one quantity to a phenomenal degree of accuracy introduces uncertainty into the other quantity. So if I measure momentum to a phenomenal degree of accuracy, I will necessarily have uncertainty in my measurement of position, and vice versa. This is absolutely not obvious. If you want to take modern physics, physics 220, 320, whatever court number, it's some 300 level physics at Niagara University. We prove relations like this. The proof isn't that bad. Right now, if you guys wanted, we would be able to do it. We would just have to spend a few weeks with some background information. But it really isn't that bad. So in classical physics, we could know position and momentum to perfect accuracy. In quantum mechanics, if you know one, if you measure the other, measuring position will kind of introduce uncertainty into that momentum, and we don't really know momentum anymore after we measure position. And that is written in the language of quantum mechanics by being something other than 0. The thing other than 0 that this commutation is equal to is IH bar. Now, H bar is the reduced Planck's constant, so that's just equal to IH over 2 pi. So I is the square root of -1, the complex number, and H is Planck's constant. So H is a really tiny number. It's of order 10 to the -34. If H were equal to a number like 1, then we would see this phenomena in everyday life, and we would be familiar with quantum mechanics. We would say that's how nature works. But because H is 10 to the -34, this behavior doesn't really become apparent until you're looking at really small objects. And so that's why quantum behavior is very often associated with the physics of the very small. So how are we actually going to measure Planck's constant in today's lab? The way we're going to do that is through using LEDs. So what's an LED? We talked about LEDs in a previous lab. An LED is a light emitting diode. So you could think of a diode like a one-way street. So if I have a circuit element with a diode, current is allowed to flow one way through the diode. Current is not allowed to flow the other way through the diode. And LED is just a diode that lights up when current is flowing through it. Now, LEDs come in different colors, like yellow or green or blue or red. Those are the 4 colors we're using in today's lab. So, the way an LED works is, this is not a formal picture of how an LED works. This is more like a cartoon of how an LED works. So here I have some electrons that are at a high energy state, and those electrons are going to be, so here we have some amount of energy, and these electrons are going to be kicked down to a lower energy state. So the electrons are kicked down to a lower energy state. The amount of energy that the electron loses is given by Q times V. So the energy difference between the high energy state and the low energy state is equal to QV, where Q is the electron charge and V is the voltage. between the high energy state and the low energy state. Now, energy has to be conserved. So if I kick an electron down here, the electron lost energy. Where does that energy go? Well, the amount of energy lost is going to be equal to the energy of the light given off by the diode. So the energy lost is given off as light, maybe green light or blue light or red light or yellow light. So this energy is emitted as a photon. So we give off a particle of light, and the energy of light is equal to h times f, where h is Planck's constant, and f is the frequency of the light. Now, in the lab, I tell you that frequency and color and wavelength are all interchangeable ideas. I give you the wavelength of the light, of the colors of light of the LEDs. You then could calculate, given the wavelength, here's how you find the frequency. I give you the equation in the lab for how to do that. So I will give you the wavelength of the light emitted for each color of diode. If you know the wavelength of the light, then you know the frequency of the light because I give you the equation. Well, if the energy lost is Q times V, and the energy of the light emitted is H times F, I could set these energies equal to each other and say that QV equals HF. QV is equal to HF. Now, from here, I could rearrange this equation and say, okay, the voltage between the high energy and the low energy state is equal to H over Q times F. So what you're going to do is you are going to you are going to calculate the frequency of the light. Q is the charge of the electron. You know what that is. You can look it up. It's also given in the lab. What about this voltage? What are we doing for voltage? Different color LEDs will be giving off different color of light. Different colors of light have different energies. Now, if a different color of light has a different energy, well, that means we have a different energy on this side of the board as well. So the charge of the electron never changes, but the voltage to turn on an LED will change depending on the color. So the voltage necessary to turn on an LED depends on the color of the LED. Blue light is the most energetic light, so if we say the energy of the light emitted that the electron loses is Q times V, this energy is given off as blue light. You will need a lot of voltage to emit blue light. Red light is low energy, so you will need less energy, less voltage to create red light. Okay, how do we know if the light is actually turned on? Because I could look at an LED, but I'm in a room with light, my eyes are not perfect, so I want to know if the LED is actually on or not. And the way we're going to address that is if I do not provide enough voltage, the electrons are never going to transition, And if I don't put enough voltage across the LED will not turn on. So there is a minimum voltage to turn an LED on. And this minimum voltage to turn on an LED, I'm just calling a threshold voltage. Or I'm calling it VT. So how can I actually determine if an LED is turned on or not? Because I'm in a room with light. The LED might barely be on, but it might not quite be giving off enough light for my eyes to see anything yet. So what's going to happen is we will take the power amplifier. So here's the black cord, here's the red cord. And I'm going to connect the power amplifier to a multimeter. And I'm going to then connect the multimeter to the LED. So here's my LED. And then I'm just going to send the LED back into the power amplifier. If the threshold voltage is not reached, then the LED is giving off no light. And if the LED is giving off no light, there is going to be no current in the multimeter. So I am going to measure the voltage at which the LED barely turns on. I will know the LED is barely turned on when the multimeter begins recording a current from something other than 0. So when the multimeter barely records a current, I know that the LED is barely giving off light, and whatever voltage the LED is barely giving off light, that is my threshold voltage. So the energy at which the LED barely gives off light is going to be this threshold voltage right here. So then I could say, okay, the threshold voltage, then that's the energy of light. And then I could rearrange this to say threshold voltage is equal to Planck's constant over Q times F. Now, the very last complication. The multimeters we are working with are very cheap. They are less than $3 each. So measuring 0 current in a multimeter is not really going to be that accurate. So instead what we're going to do is we're going to presume that instead of saying it's 0 current exactly, let's say the current is less than 0.2 microamp for more than 30 seconds. The smallest current the multimeter can measure above 0 is 0.1 microamp. So I'm going to give the multimeter a little bit of wiggle room. So I'm going to say that the multimeter has to measure less than 0.2 microamp for at least 30 seconds. Because sometimes you measure a current and the current might jump around a little bit when you're doing a very fine measurement. So if it's 0.1 microamp, 0.1 microamp, 0.1 microamp, 0.1 microamp, 0.2 microamp, 0.1 microamp, 0.1 microamp, on and on, I want to make sure it's just not jumping above 0.2 very often. So as long as we are approximately 0, we'll be very close to the threshold voltage, and that will be okay. So what we did in this lab, and again, read through the lab, is we are measuring with the multimeter the voltage. We are measuring on the power amplifier on the Data Studio software. At what voltage will we barely have current barely flowing through the multimeter? And when current is barely flowing through the multimeter, that means the LED is barely turned on, the electrons are barely making that transition. And if the electrons are barely making that transition, the LED is barely giving off light. So I gave you everything you need for this lab. I took the data for this lab. So if there's anything at all you want to ask about this lab, just send me an email. We could teleconference. And ultimately, what we're trying to do is we are going to make a plot of threshold voltage as a function of frequency. And so if I plot threshold voltage as a function of frequency, here is my threshold voltage, the voltage at which the LED barely turns on. Here is the frequency. Frequency is just another way of saying color of light, but a quantitative way to say color. Think about what shape this plot should have, and think about how Planck's constant fits into the shape of this plot. We assume we know the charge of the electron. F is something we could calculate because we know the colors of the LEDs and we know the wavelengths of the LEDs. And VT is something else we calculate. So we're going to make a plot of the data points, and we're going to then fit this plot to try to determine a value for Planck's constant. And for this lab, if you get a correct order of magnitude, so if you ultimately, Planck's constant is 6.636 times 10 to the negative 34 joule seconds. If you get something multiplied by 10 to the negative 34, for this lab, that's pretty good. So our accuracy will not be phenomenal, but we are going to get a good order of magnitude estimate for this fundamental constant of nature where quantum behavior becomes observable. Current from the power amplifier is going into the multimeter. The multimeter is currently set to measure DC amps, and for a while the current passing through the multimeter has been hovering barely below 0.2 microamp, so we've had a very small current for a while. Current will go from the multimeter into the breadboard. Now technically the LED on the right is barely turned on, but the LED is not giving enough light off for us to actually detect. However, we do know that the LED is on because technically there is a current flowing through the LED. There's just so few photons being emitted by the LED that we cannot detect it with our eyes. And then the wire is connected back into the multimeter. So right now, this light is barely turned on at a voltage of 2.265 volts. So I enter 2.265 volts onto my data table, and I get something that looks like this. So this is my data collection for this lab.